So we know the structure of the phenol. This is of what we call the molecule phenol. Let us see the preparation, and at the end we are going to discuss some important interconversions and the problems. So first one, how to prepare this phenol, preparation methods. Preparation of phenol. So in that first one, from cumin. Cumin is nothing but the isopropyl benzene. So how to prepare this phenol from the cumin means, we'll take the cumin. This is the cumin. But usually what they don't separately write down this hydrogen. They write down hydrogen here. This is we call cumin. So this cumin, its another name is isopropyl benzene. So this cumin, when subjected to the O2 oxidation in the presence of the sunlight, second one followed by concentration of some H2SO4. See, from here onwards we don't discuss the much mechanisms, as the mechanisms are not important to you. So because if you concentrate more on the mechanism, that shall not be useful for you. We get the phenol plus acetone. Whatever the mechanisms are important that we have discussed in the reaction mechanism, that you please follow it. Phenol, and this particular part will be oxidized to the acetone. So in this way we can prepare the phenol. There are many other methods. Let us see one by one here. The second method is Douse process. Douse process is so important. I'll explain it later. Okay, I'll explain here only, is just to see why Douse process is so important. So in this Douse process, take the chlorobenzene. I'm not writing the text matter, as this video will be available to you so that you can see it later anytime. Chlorobenzene, NaOH, 300 degrees centigrade and 300 atmospheric pressure. We get the phenol. Why this Douse process is so important? Because this Douse process is the process in which benzene participate in the nucleophilic substitution reaction. Do you know actually benzene participate in the electrophilic substitution reactions? But in this reaction, benzene participate in the nucleophilic substitution reaction because OH minus replaces the chlorine, Cl minus. So one nucleophile replaces another nucleophile and giving the phenol. And how could this happen means, it is simple thing that here we are using the very drastic conditions. 300 degrees centigrade temperature, 300 atmospheric pressure. 300 atmospheric pressure means it is 300 times more pressure than the our normal pressure. So that's why under these conditions, benzene even participate in the nucleophilic substitution reaction, and Douse process is an example for the nucleophilic substitution reaction. And in phenol properties, we shall discuss once again. Here I'll explain one more important thing to you. That is regarding the if you put chlorine here, NaO2 group, okay, and use again chlorine 2 nitro groups and chlorine with 3 nitro groups. Why I am explaining these three reactions is, When you use this much only chlorine without nitro groups, means if any electron withdrawing group is there, the nucleophilic substitution reaction takes place uh, very easily. Otherwise, we need to use the drastic conditions. Now, in these conditions, you no need to use much pressure, much temperature. Here, just use NaOH with 200 degrees centigrade, some 60 to 70 atmospheric pressure. That's enough. So here you will get the OH and NO2. And here, if you use NaOH in normal room temperature, 25 degrees centigrade, because two groups are there, even normal atmospheric pressure. So here you will get this particular molecule. Means OH can easily replace the chlorine when electron withdrawing groups are there. Now in this condition, even you don't need even the help of NaOH, just use the H2O enough. Means water is actually weak nucleophile than the OH minus ion. Even water molecule is able to replace the chlorine from that benzene ring and able to provide this particular molecule. Okay, and among these molecules, the name of this molecule is picric acid. Picric acid, and interestingly, this is the compound whose name ends with the acid without acid group. No COH group is present, but still it is a called as the picric acid because of electron withdrawing groups. This molecule is so stable so that it can release H plus and with very ease. So that's why it is called as the strong acid, and its acidity is nearly equals to the normal acids. So that's why it is a strong acid. And one more is this is not so good compound, so that if you apply it to your hands, the hands turns to yellow color. Even later, if you apply, use that hands to rub anywhere in your head, over your head, your hair completely will be removed. Not only your hair, anybody's hair. So these are all best example for the nucleophilic substitution reactions. This is called the Douse process. These are not the Douse process, applications of the Douse process. Now let us see how to prepare the phenol from the diazonium chlorides. That is third one, benzene diazonium chloride. From benzene diazonium chloride. So you just take the benzene diazonium chloride, N plus, and here Cl minus. This is called as the benzene diazonium chloride. Subject with H2O, H plus, and heat it. You please remind me during the nitrogen amine aniline compounds. Benzene diazonium chloride has very vast applications. If you want to prepare any benzene compound, and we used to convert that initial benzene to the benzene diazonium chloride, it's very important compound. So that this is so diazonium chloride is so good leaving group, so that any weak nucleophile can easily replace that. So here electrophilic substitution reaction. So here we get the phenol. This is benzene diazonium chloride. I don't want to write that once again. Okay. Now let's take the benzene sulfonic acid. From benzene sulfonic acid. So in benzene sulfonic acid, this is benzene sulfonic acid when subjected to the fused KOH. So here also we get the phenol. Sulfonic acid, when you add fused KOH, not only KOH, even if you add water also, that's enough. Sulfonic acid can easily be converted to the water. Now the interesting reaction is coming now. The reaction is Dawkins reaction. Please remember these reactions, or else write down all the named reactions in 4 to 5 pages at particular place. Dawkins reaction. In this reaction, we take alpha hydroxy carbonyl compounds. It may be aldehyde or ketone. So that when subjected with the H2O2 in the presence of H plus, second one H2O in the presence of H plus. Sorry, this is OH minus. It is responding so slow. So alpha hydroxy aromatic aldehydes and ketones shall be converted to their respective diols. So OH group and here also OH group. So here the condition is OH group must be at the alpha position, ortho position. Okay. So here I'll write orthohydroxy carbonyl compounds shall be converted to the uh, diols, OH groups. So ortho or para. One more is there condition. It may be at ortho position or at para position. So OH group must be at ortho position or para position. Let us take another compound. Here what shall I take? I'll take keto group. Now here I'll put the OH group at the para position. So OH group is at the para position or ortho position, so that the entire group shall be converted to the OH group. So this is the importance of the Dawkins reaction. Now let us see the chemical properties of this phenol. So in the chemical properties of the phenol, first we need to discuss the acidity. So in acidity of the phenols, when you compare the acidity of the phenols with alcohols, normal alcohols, see this is the normal alcohol. When it lost H plus ion, it provides the alkoxide ion plus H plus ion. This is alkoxide ion. So any compound acts as an acid whenever its anion is stable. Now let us take the phenol. And it lost H plus ion plus H plus ion. Okay. Now here, if you see, this is the phenoxide ion. Okay. Phenoxide ion, the negative charge in the phenoxide ion can easily be undergo delocalization. So delocalization is possible so that it is stable by resonance. And here such type of resonance is not possible. So alkoxide is unstable. Since it is unstable, immediately accept the H plus ion, so that reaction is more favorable towards the formation of the alcohol rather than the formation of the alkoxide ion. But in this case, phenol, if you take both phenol and phenoxide ion, uh, it is favorable more towards the formation of the phenoxide ion rather than being in the form of the phenol. I'll explain here two reasons why phenoxide ion is more stable than the phenol. That's why phenol is a strong acid. I shall explain both the conditions so that you should not get the doubt later. See here, initially we take the phenoxide ion. So in this phenoxide ion, the negative charge participate in the resonance, delocalization. Like this, again shifting of these negative charged electrons. So that it comes like this, negative charge is here and the negative charge comes over here, and shifting again to the other position. Negative charge, again it comes here, and finally it goes there. Phenoxadiam, it is having these many resonance structures, almost 5 are there. Okay, and now let us see why phenol is unstable than the phenoxadiam. Let's take the phenol. In phenol, lone pair of electrons are present over the oxygen atom. So these lone pair of electrons participate in the resonance. Negative charge, it comes over here, again shifts over there. It goes like this. Negative charge, and finally it comes over here and it goes there. Now, among these two resonance structures of phenoxadiam and phenol, you can observe one important thing, that in this case oxygen is getting the negative charge. Afterwards, negative charge is delocalized among all the carbon atoms. Again, finally, the negative charge has come and sat on the oxygen. But if you see the same thing, the negative charge is over on the positive charge is on the oxygen in all these resonance structures. Means out of 5 resonance structures, 3 resonance structures of the phenol is having the positive charge on the oxygen. Oxygen is the more electronegative element, so that cannot tolerate this positive charge over it, so that it always ready to lose this positive charge by gaining electrons to back. Hence, this phenol cannot develop these many type of the resonance structure. These are all unstable resonance structures, but in the case of the phenoxadiam, these are all stable resonance structures. Hence, phenol always ready to lose the H plus n and to be in the form of the phenoxadiam, which gives the more stable to its structure. That's why we say that phenoxadiam is more stable than the phenol. I'll write here. Phenoxadiam is more stable than the phenol. Okay. Now, let us see some of the properties of this phenol. And before discussing the phenol, you need to see here, phenol undergoes electrophilic substitution reaction at ortho and para positions. So you can see here, the negative charge is developed at the ortho position, para position, again at ortho position, because the OH group lone pair of electrons are delocalizing into the ring. That's why OH group is called as the ortho and para directing group, because whatever the electrophile you are going to add, that electrophile will be attracted to the either ortho position or to the para position or again to the ortho position. So it is a ortho para directing group. So we can say that OH is a ortho and para directing group. So whenever you write down the structures of the phenol, you will get only ortho products, para products, or both, not the meta products. So you please remember that. So we shall see some questions here, some examples. Very interesting examples are there. This is the phenol having lone pair of electrons in it, and now subject this phenol with the FeCl3, which is one of the important finest reaction. This is called the alcoholic FeCl3. Some people call, or some people call it the neutral FeCl3. What is the use? FeCl3, in FeCl3, Fe is having the +3 oxidation state, and OH phenol can lose this H plus ion, so that it can create the negative charge. So after the formation of the negative charge, we get the phenoxadiam. This is the phenoxadiam. Okay, 3 phenoxadians like this. This is the phenoxadiam, and you can write like this. 1 minute. Fe. This is called this is a violet color precipitate. Violet color, or else it can be written as FeC6H5O. When you don't mention the negative charge, when you mention the O, then you have to show the positive charge. 3 plus 3. So phenol reacts with the neutral Fe3 and gives the violet color. This is the test to identify the presence of the phenol. So remember that. And phenol, when subject with the NaOH, since NaOH is a base, this is an acid, forms the phenoxadium, sodium phenoxide. And phenol, when subject with the CH2En2, diazomethane, in the presence of the sunlight. This discussion we have done. Diazomethane are ketenes. They are the methylene, they substitute methylene group. So they substitute methylene group between the oxygen and hydrogen. Already hydrogen is there, here 2 hydrogens are there, it becomes the CH3. So you will get the molecule OCH3. Then subject this phenol with the CH3 C double bond OCl in the presence of the pyridine. This is acid chloride, or you can use the acetic anhydride also, CH3 C double bond O C double bond O CH3. You can use this one in the presence of the pyridine. Basically, this is the alcohol group, these are acid compound, so they form the ester. O C double bond O CH3. Then the question arises, what happens if the phenol is subjected with the DMSO, dimethyl sulfoxide, or we don't use the dimethyl sulfate, I'll take. In the presence of NaOH, it gives the same molecule. OCH3. Okay. So these are some reactions. Now we shall discuss some other important reactions. So the other important reactions are alkylation reaction. So in this alkylation reaction, you just take the phenol and add allyl bromide. In the presence of NaOH, here hydrogen bromine shall be removed. So we get the OCH2 CH double bond CH2. This is allyl part, this is the phenyl part, and it is ether. So we call it as a allyl phenyl ether. And interestingly, if you just heat this molecule, allyl phenyl ether, no need to just heat it, and it undergo automatically internal rearrangement and it gives CH2 CH double bond CH2. Means this carbon shall be connected here, not this carbon. It looks that the CH2 CH double bond CH2 has been disconnected and connected over here. No, not like that. This pi bond will be shifted here, and these pi electrons will go there, and the rearrangement will take place like this. Okay, heat to the nearly 200 degrees centigrade. Why I said this reaction is important is it has its own name. The name is Claisen rearrangement. Only this step, not this one. Claisen rearrangement. Now, let's take acylation nature. Means already we have discussed this reaction just now. Phenol, you just subject this phenol with the Cl, C double bond O, CH3 in the presence of NaOH. It will lose this HCl minus HCl. So we get the ester molecule O, CO, CH3. It is one of the important reaction which we are going to discuss. This is the phenyl ester. Okay, and this phenyl ester, if you heat it, I repeat you just remember this structure. Benzene is having the oxygen, not the CO group. So here CH3 may be any group, it may be R actually. So when it is subjected in the presence of the anhydrous AlCl3 and heat it to the 160 degrees centigrade, this is high temperature, and 60 degrees centigrade, that is low temperature. So when you heat it to the high temperature, the COCH3 group shall be transferred to the ortho position. OH, C double bond O, CH3. If you use the low temperature, this shall be transferred to the para position. And this is there in your syllabus. NEET syllabus, this reaction is there. So this reaction is so important, and the name of this reaction is freeze rearrangement. Freeze rearrangement. Now, let us see some other electrophilic substitution reactions of phenol. Just take the phenol. Means I am writing like a chart. So this phenol, when subjected with the concentrated HNO3, and dilute HNO3. When you use the concentrated HNO3 and H2SO4 mixture, then all these ortho and para positions shall be occupied by the NO2 group. OH, NO2, NO2, and NO2. This is called trinitrophenol, which is called as the picric acid. If dilute HNO3 is used, then either ortho position or a para position shall be occupied. So you will get the two compounds, orthonitrophenol as well as the paranitrophenol. So concentrated and dilute. Similar reaction I shall explain one more, as these two reactions are so important to you. When you use the bromine in the presence of the water, because these reactions have been asked many times, and bromine in the presence of the CCl4. When you use the bromine in the presence of the water, all the three positions are occupied by bromine. So we get the tribromophenol. Similarly, when you use the CCl4 as a solvent, then ortho and para positions are occupied. Orthobromophenol and parabromophenol. That's why I said these reactions are so important. Now let us take the another similar reaction. that now you subject this reaction phenol with the H2SO4, only H2SO4, and temperature. This is at 100 degrees centigrade high temperature. This is at 25 degrees centigrade low temperature. So when you use the high temperature, you will get the para-hydroxybenzene sulfonic acid. This is the as the major compound. Both will be formed in both the cases. And if low temperature is used, OH, SO3H as the major compound. Here also this compound will be formed. Here also this compound will be formed. But major is para here and major is ortho there. Next, let's see some two more reactions. Phenol on reaction with the CH2 taken 6 N4 KOH H2O H plus heat. You should remember this reaction. This name of this reaction is a Duff reaction. This molecule is called as urotropin. It is also called as hexamethylene tetramine. Hexamethylene tetramine. It is used for the urinary infections. Okay. So when this particular molecule is used, we get the phenol here, OH here, CHO. Why I said this reaction is so important is a similar compound you will get. Reactant product will be same, and up to this particular reagent is also same. Only by changing this reagent you will get the same molecule. That is, you put CHCl3, KOH, H2O, H plus. Okay, and the name of that reaction is, this is called the Riemann reaction. So if you remember one reaction, then you can remember another reaction also. Just only difference is here chloroform, here urotropin, hexamethylene tetramine. Apart from that, now when phenol is subjected with the HNO2, nitrous acid, or else I said many times that it is a combination of NaNO2 and HCl. So you will get the orthonitrophenol and para-nitrophenol. This is para compound. This is ortho compound. Now use the zinc ZnCl2 in the presence of HCN and H2O. Again the same molecule you will get it. OH, CHO plus even ortho product, para product also shall be formed. So if anyone asks you how to get this is salicylaldehyde. It is not working properly. So here it is a salicylaldehyde. Okay. So salicylaldehyde from the phenol can be obtained in three ways. One is Duff reaction, Riemann reaction, and zinc chloride HCN. So you remember these reagents, three reagents, then you will get the same molecule. So you need to synchronize reagents here. Next, let us see Riemann reaction separately. Riemann reaction, just I am explaining, and do not by heart this reaction. Mechanism is important for this reaction. That's why this reaction mechanism I will explain. So we know that we take the phenol, it is added with the chloroform with an AOH or KOH. This is the step 1. Step 2 is H2OH plus. Then here we get the salicylaldehyde as the major compound. Here also two compounds will be formed. This is a major compound and minor compound is one more is there. OH, CHO, this is the minor compound. Okay. Now let us see the mechanism here, as the mechanism of this reaction is a bit important for us. So let us see the mechanism. So in the mechanism, first step is the reaction between these two. You just see here hydrogen, this is one chlorine, this is another chlorine, this is another chloroform, tetrahedral shape. So OH minus is used. The question is here chlorine carbon, chlorine is more electronegative than the carbon, so that all these chlorine gets the partial negative charges, carbon develops the partial positive charge. Okay, so because it is having the more positive charge, carbon withdraw the electrons from the hydrogen. So now hydrogen is more vulnerable to the attack of the OH minus. So OH minus can easily attack over the hydrogen and these electrons will be shifted over to the carbon. So we get C minus Cl3 and here H2O molecule has been left. Okay, and this C minus Cl3 will lose one more Cl minus ion. It is losing the Cl minus ion. So I'll inform you one more thing, that chlorine, 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 negative charge means 2 electrons are there. So now when chlorine with electrons, if it is left as a chlorodiam, now carbon is having these 2 electrons with these 2 chlorine bonds. So CCl2 2 electrons means 1 2 3 4 5 6, around it only 6 electrons are there. So it is an electron deficient species. So electron deficient species because it is having the sextet electronic configuration. Since it is electron deficient species, it is an electrophile. It is seeking electrophiles now. Electron. So it is an electrophile. Since no charge is present over this, because electrophiles means positive charged species are called electrophiles. Here no such charge is there, so it is called the neutral electrophile. And the name of this CCl2 is a dichlorocarbene. So chlorocarbene is the neutral electrophile in Riemann-Tiemann's reaction. So now let's see the remaining steps. So in the remaining steps, actually we take the I am taking directly phenoxadiam. Why? Because you can take the phenol also. One more step it will be. If you take the phenol, nothing will happen. This OH minus and still present in the reaction mixture. So that since it is an acid, it is a base, it attracts the H plus ion, so shall be removed as the H2O. And finally, we get the phenoxide again. So this phenoxide ion will be attacked by the dichlorocarbene. C, Cl, Cl. How will it attack? Means these electrons will be shifted over here. This electron will attack over here. Here two chances are there because we have written here para product also we have written. This is the para product. Para product also we have written there. I'll explain how the para product will come. Here only I'll explain. I'll take the same molecule, this species, phenoxadiam. So O minus. Now again CCl2. Now these electrons will shift and these electrons will shift over here, and these electrons may attack. So when these electrons are attacking, these electrons are attacking through this carbon, and when these electrons are attack over this through this carbon. Okay, so when it is attacking through the ortho position, now here we'll get the hydrogen. Since electrons are shifted over here, this carbon gets the negative charge now. Because carbon is not sharing its electrons with this carbon. Because the pi electrons are attacking over the carbon, and this lone pair of electrons remain in the carbon as it is, just like here. Okay, so this carbon will have the negative charge now. Now, if you see one important information, that is, this is an aromatic compound. This is not aromatic compound. Aromatic compounds are stable. This is unstable. So a stable compound has been shifted to the unstable compound. So what it will do immediately, it will ready to get its aromatic character back, because to get the stability. So for that purpose, it has to lose this H plus ion. So for that purpose, what it will do is, this negative charge will attack over this hydrogen, and these sigma electrons will shift over between these two carbons, and these pi electrons will shift over to the oxygen. Negative charge with CH, Cl, Cl. Now again, this OH minus is, starting OH minus nucleophile. So two nucleophile can easily attack over this two chlorines. They have to remove these chlorines. Here O minus, CH, OH and OH. So whenever two OH groups are on the same carbon, it is unstable. It will lose again water molecule. O minus, CHO. And in the last step, if you observe one thing, that we used the H plus, H2O H plus for protonation purpose. So H plus, it gives OH and CHO. This is salicylaldehyde. And the same procedure, if it happens over here, procedure will be same. Apart from this molecule, remaining everything is same. But apart from the ortho position, we have to put at the para position. Okay. The important one more thing here is, sir, what happens if any of these ortho positions are occupied, whether we get the salicylaldehyde or not? See, this molecule is called the salicylaldehyde. This is not the salicylaldehyde. Orthohydroxybenzoaldehyde is called the salicylaldehyde. This is just called the parahydroxybenzoaldehyde. Okay. So if any ortho position, if at least one ortho position is occupied by any other group, then CCl2 will attack over the para position. So note, if any of the ortho positions are occupied, then electrophilic substitution takes place at para position. I'll take these examples also now. So ortho position is occupied. Now use the CHCl3 KOH H plus H2O. Then major product is at the para position. This is the only product. What happens if para position is occupied? Same combination of the reagents. Then you will get the ortho position. Okay. So, and in this case, CHCl2 is there, no? So here you will get one more product also. Chances, this is a minor compound, but this compound is very less. So people get doubt how this compound could be formed. Simple thing that via para position, like this here. So if electrons, those CH3 group is here, these electrons may shift over there. So I'll write down that group also here so that you can understand. See, like this. Imagine phenoxadiam, just I am taking directly phenoxadiam, and here CH3 is there. Imagine CCl2 lone pair of electrons are present. So if it attacks over here, these electrons will shift over there, these electrons will attack over there. H plus so not H plus, OH minus. So I'll take both H plus and H2O. So H plus and H2O means H2O, OH molecules will replace this chlorine. Later H plus N will attack and finally we get the aldehyde. So chances are like this. But this is a limited quantity because generally ortho para position is occupied, it is crowded. So that this position generally not will be selected by this CCl2. Now let us give question arises. Sir, what happens instead of CHCl3? Instead of CHCl3, if I take CCl4, then what must be the product? It is simple. Then you will get the carboxylic acid. I'll show you here. The reason here is when you are using the CHCl3 chloroform, what is the electrophile? CCl, dichlorocarbon is electrophile. So there are two chlorines are there. If you use the CCl4, here CCl3 will come. So here three chlorines will come. So OH groups, three OH groups are required to replace all the three chlorines. So that I'll show you now. See what happens if OH minus, let's take phenol directly. CCl4, KOH, H plus and H2O, OH, COH. This COH comes because we get this phenoxadiam and chlorine carbon with three chlorines. All the three chlorines are to be replaced by three OH minus groups. So we shall get OH minus and carbon with OH, OH, OH. Three OH groups are there. So whatever the number of OH groups it may be, one H2O molecule shall has to be removed. So that if we remove one H2O molecule, then what is left? COCH, COOH, COOH, O minus COOH. Then transfer of proton takes place from here to there. OH, COO minus. Why? Because a carboxylic acid is stronger than the phenol. Then we use the H plus ion. so that we get the salicylic acid. Okay, the name of this reaction is Riemann carboxylation. Because carboxylic acid is formed, no? So it is called the Riemann carboxylation. If chloroform is used, that is simply called the Riemann reaction. Let us see some abnormal Riemann reactions. So in this abnormal Riemann reactions, let us take pyridine. So when this pyridine is subjected with the CHCl3 chloroform, OH minus, H2O, H plus, then you will get the two products. This is normal Riemann reaction, normal product. But abnormal product is this is abnormal product. So people get the doubt how to get this particular abnormal product. Okay, so let me show the mechanism here. It is simple. I'll take the pyridine first. Lone pair of electrons are present, and just use the OH minus and which abstract this proton, and electrons will be shifted over there. Negative charge. Okay, to this the CCl2 has to attack CCl2, and here also CCl2. Okay, so CCl2, if it attacks it here, two things will means in two ways it will attack. I'll write the CCl2 will be attached to this double bonded carbon in both the positions. Nitrogen with a negative charge here, carbon carbon bond, Cl Cl. Addition takes place. Carbon, chlorine, chlorine. So from here the mechanism is different. The mechanism goes in such a way that these electrons will shift here, okay, and here these electrons will shift over there, means the disconnection of this ring. So finally what happens, the ring will expand in such a way that this is a nitrogen, next this is a 1 carbon, 2 carbon, 3, 4, 5. So the molecule comes like this. Nitrogen is there, nitrogen has developed one bond here, pi bond, and these sigma bond electrons are disconnected and the bond is shifted between these two carbons. So here pi bond comes, and this pi bond separated by this single bond. So next bond is here, and afterwards one more bond has to be left, next one more bond like this. And at which position these chlorines are there? One chlorine will be removed because carbon valency crosses the 4, no? So that's Cl minus. So 1, 2, 3, 1, 2, 3, third position chlorine comes. And how this normal product is coming? When electrons shift this side. So here this particular bond, whatever the bond is there, this bond will break. Now this is not the aromatic compound. To get the aromatic character, this negative charge will attack over here, and these pi electrons I'll write that side. attacks over here. This pi electron shifts over here. This pi electron shifts over. These pi electrons will shift over there. Here negative charge. Now 2OH minus and loss of water molecule. CHO. Now protonation. H plus H2O. Okay, this is the product. So this reaction is so important for you. This is abnormal product. It was asked many times in the previous examinations also. Now let us see the Kolbe-Schmidt reaction. So in Kolbe-Schmidt reaction, our main target molecule is again phenol. So this phenol, we take the carbon dioxide, NaOH, H plus H2O. The molecule is salicylic acid again. This is the major compound, salicylic acid, plus its respective para compound also shall be formed, which is minor. And the same compounds again we get by using what other reagent? Just instead of the CO2, use CCl4, NaOH, H plus H2O. We had already named that reaction here. That is Riemann-Tiemann carboxylation reaction. See here, we have shown the Riemann-Tiemann carboxylation reaction. Okay. So you have to compare always, means when you are having the same reactant and same product, when reagents are different, then try to read those reagents together. Then only you can easily understand. And let us see some other important reactions. Oxidation of phenol. This was asked many times in the even objective examinations also. Oxidation of the phenol. We take the phenol. Means when you change the oxidant with air or HNU, sunlight, just if you put the phenol in open bottle, then this phenol will be oxidized to the parabenzoquinone. Brown colored compound. So they asked the question, why phenol is converted to the brown colored compound when it is put in the air open bottle? Because it is oxidized to the parabenzoquinone. Oxidation means loss of hydrogen. How this is losing the hydrogen means very simple. I'll show you here. It is not getting selected today. Yeah. See here, the bonds are like this. Okay, I'll write separately. So how this is coming means hydrogen OH. So the bonds will be shifted like this. This pi bond, this pi bond, and it will come over here. So hydrogen will be out. Here air is there in oxygen. This oxygen is from the air. So these pi electrons will shift over here, and this will be shifted over here, and later this bond also will be disconnected. Like this means basically hydrogen from here, hydrogen from here. Two hydrogens are removed. Next, One of the important reaction here it is K2S2O8 with OH minus. Now oxidation product is different. OH here and OH here. This is called as the paraquinol. So when normal air means parabenzoquinone or persulfate, potassium persulfate means it is a paraquinol. And two more reactions are there. After two reactions, I'll stop this class, and tomorrow we shall discuss the one important objective questions. Reaction with zinc dust. This everyone knows. If you use the zinc chloride, that is different. It is the benzaldehyde. So zinc dust means you get the benzene, zinc oxide. But ZnCl2HCN means you get the OH and CHO. So these are the products. Now the last important reaction, LM reaction. This reaction, if you want, this is not there in your NEET syllabus. It is the Lateral Manasseh reaction. So in this reaction, the major things are we take the phenol, but in between products are not important. First product and last product are important for you. When phenol is subjected with the formaldehyde in the presence of the H plus and H2O, the use of the formaldehyde is methoxylation. Methoxylation means it will put CH2OH. This we have studied in the Prince reaction also. You can search that Prince reaction. Okay. So here OH group, CH2OH group, and that CH2OH group shall be placed ortho and para positions. So any of these positions it will put. Interesting thing is only first product is important. Again last product is important. Middle products are not important. When it is reacted again with the formaldehyde H plus H2O, and this is also when subject with the formaldehyde H plus H2O. In this case again you will get the CH2OH group here, and in this case you will get the CH2OH group there. OH, CH2OH, CH2OH, so OH, CH2OH, CH2OH. Now both the products are same. So again these compounds reacted with each other. On reaction with each other, sorry, not reaction with each other, they react with the formaldehyde in the presence of the H plus and H2O, because in both the compounds only this ortho position is vacant, so they get the same product now. OH, CH2OH, CH2OH, CH2. This product is so important for us in the polymer reactions. Why I am saying this is so important is when this compound is subjected to the H plus acidification, so it will take similar molecules like this. OH, CH2OH, CH2OH, CH2OH plus OH, CH2OH, CH2OH, CH2OH. Like this you can take n number of molecules in all the directions. Here you can take, here you can take, here also you can take. So when you take these molecules, the thing is H2 will be removed. So when H2 is lost, then what must be the molecule, final molecule? Just guess it here. It is so easy. This molecule here, phenol, CH2. Okay, so CH2 connection is this side, it will go like this. And bottom side also, if same molecule in reverse way, this molecule if reacts here, here also you will get this CH2 connection. And this side also, if one more molecule reacted this molecule with this molecule, you will get this CH2 connection. Means this becomes the repeating unit in this particular reaction. And this is the polymer. This polymer name is, you know already, it is a bakelite. So it is a preparation of the bakelite. So bakelite can be prepared by using this type of reaction. Anyhow, this video will be available for you just to see it. And at the end, I'll give some important brainstorming questions to you. I request you all just try to solve. First question. You write down all your possible products. H2O. B. Because these reactions are a bit important to you to understand the sequence of reactions. So you must understand that here some product is there. That product again reacted with this molecule and giving this particular final product. Pyridine. So here you will get some product A. This on reaction with the AlCl3 you will get the B. This B on reaction with NaOI gives the C. This NaOI, we had made one particular video about this one haloform reaction. You first see that haloform reaction video, then solve this particular. If you are having any idea about this particular haloform reaction clearly, then you can solve that question. So these are the 1 minute. It is not getting. So these are the 3 questions. I request you please solve these questions.